Our names are Artur, David, Kewei, and Tudor, and this is our CS51 final project, Handwriting Recognition. Handwriting recognition is an exciting application of machine learning algorithms which has direct relevance to industry, whether that is scanning addresses at the post office or recording medical notes at the hospital. In addition, this project offers insight into image processing, neural networks, and trainable algorithms at large. Let me begin by giving you an overview of our project. This project includes three key parts: image processing, training our neural network, and finally testing that neural network. Image processing begins with cropping. Cropping involves removing any superfluous white space to the left and right of the image. Next, we will separate the letters. To segment letters, we search for white space. Here is a graph of the relative dark space saturation at each vertical slice of the image. You can clearly see where the separations between letters are on this graph, and we track the percent change in dark space saturation to segment letters. In the case of multiple words, we use a simple k-means algorithm to differentiate spaces between words from spaces between letters. Next, we crop any superfluous horizontal white space to standardize the size of our image. Then, we process the image by converting it to grayscale. We make n vertical and n horizontal slices, and then finally average the pixel values in each of the newly formed rectangles. We have now converted an image into a matrix of parameters to be passed into the neural network.
A neural network is a graph-like data structure in which nodes are organized in layers. Each node will contain a numerical value that it will feed into the next layer of neurons. The first layer of the network will be the input layer, which will be the list generated by the image processing algorithm for each image, while the last layer will be the output layer, in which every node will represent a character to be recognized. Every other layer will be called a hidden layer. A trained network should take the list generated from an image of a character and output a list in which the node corresponding to that character is singled out, close to a fixed value, say 1, while the others will be close to 0. In each layer, each node is connected to every node in the next layer. Every connection is characterized by a weight. Basic functionality of a node is that it takes the weighted sum of the outputs of the previous layer and passes it through an activation or transfer function. In the supervised learning algorithm called backpropagation, we start with a network with random weights and compare its output with the desired output for each input. The difference between the actual value and the desired value will be calculated backwards through the network in a linear manner according to the weights, so that each node will have a delta, which means an error. The sum of squares of deltas, the capital E function, will be viewed as a function of all the weights leading to that layer. The weights will be updated by gradient descent to converge on the smallest error possible. The step of the linear descent is called the learning rate. The process will be repeated until the desired accuracy is obtained. Our training set consisted of 50 sample black and white images for each character, just like the one shown here.
Let's pull up the GUI for a quick demo. First, we choose an image. Then we choose a mode, so for this we do lowercase, and then we hit run it. It computes a guess at what the thing says and a confidence.
Finally, we statistically analyzed our network to optimize it. From this graph here, you can see that with the appropriate learning rate and just 100 iterations, we achieved a confidence in desired output of well over 90%. A graph of confidence in desired output versus number of neurons in the hidden layer shows a plateau around 20 neurons. This motivated our decision to minimize the number of hidden layers at 20 neurons, which helped reduce our training time. Finally, we optimized the number of input parameters we are using by charting the prediction confidence versus the number of input parameters. We are happy to report that we achieved a 97% accuracy for only digits using our neural network approach. Thank you for listening.